In this video lesson, we are going to look at Theorem 1 to 2. And before we begin, I just want to remind you how we do mathematics. Now, first of all, make sure that you understand each step. And especially for these videos that we are going to do now, where we're going to look at the proofs of some of the theorems, don't just learn the proof off by heart without understanding the steps. These proofs, some of them are examinable, so it's just easier to learn them if you basically know what's going on. Okay, and then obviously when you see the pause button, make sure to pause the video, do it on your own, and then play it and mark it. And then when you mark it, make sure that you understand where you made your mistakes so that you know not to make the same mistakes the next time. Now, an overview of what we're going to be looking at. First, we're going to do Theorem 1 and then Theorem 2. So in these sections, we are only going to look at the theorem itself and also look at the proof of that theorems and the inverses or the converse of Theorem 1. And then finally, in the last section, we are going to do question sums and the application of the two theorems. Okay, so for Theorem 1, it says that a line drawn from the center of a circle perpendicular to the chord bisects the chord. Now, to understand what's going on here, let's say you are given a circle, and the only thing that you are given about the circle is that O is the center, and then there's a chord drawn in the circle, and the chord can be anywhere, any length, anywhere in the circle, as long as it touches the radius at 2 points. Now, the only thing they tell you is they tell you to draw line OY, but you must draw it in such a manner that OY is perpendicular to XZ. Okay, so if you do that, if you draw that line perpendicular to XZ, what's going to happen if you measure XY and you measure YZ, the lengths are going to be equal. So this is basically what this theorem says. It's if this line from the center of the circle to the chord is by perpendicular to XZ, it means it's going to bisect the chord or divide it into two equal parts. Okay, so that's basically it. Then the reason that you state, if you ever use this in a question, the reason for that statement will be a line from center perpendicular to chord, because you have to use the official reasons. You can't just write something that sounds like the reason. This is the official reason that you need to write down when you use this theorem. Okay, now I want us just to kind of make this idea a bit more flexible in our heads. So what I'm going to do is I'm going to move the chord around so that we can see what will happen if the chord lies somewhere else. But the only condition we know is that the chord and the line from the center of the circle has to be perpendicular. So when we move that chord around, we can see as long as we keep that line perpendicular, it's always bisecting the chord. Okay, and that is basically making this theorem true. So as long as the line from the center remains perpendicular to the chord, it will bisect the chord. Now the second thing I want to show you is what if it isn't 90 degrees. So if we take it and we move the chord so that it is no longer 90, you can clearly see that either DF will be greater than FC or FC will be greater than DF when we move that around and it's no longer perpendicular to each other. Okay, now let's look at the proof of Theorem 1. So here is our sketch. Then what are we given? First of all, we're given that O is the center of the circle. And the second thing that was a condition is that OY must be perpendicular to XZ. Okay, so those two things we are given. And then from that, we need to prove that if we have drawn a line OY which is perpendicular, that line will always bisect XZ. In other words, to prove that it's going to bisect it, we can basically prove that XY will be equal to that YZ. Okay. Now, the first thing we're going to do to prove it is we're going to construct a line OX and OZ. Now, before I go into the proof, I just want to talk through what we're aiming for so that we don't just go line by line and you don't know where we're going with this, okay? So first of all, we have constructed those two lines so that we can create two triangles, okay? And in geometry, when we want to prove like two lines equal to each other, one of the methods, okay, which is quite common commonly used in geometry. One of the methods to prove two lines equal to each other is you can kind of do those two lines lie in two separate triangles, all right? And if they do, can you prove those two triangles congruent to each other? Because we have learned about congruency and similarity in grade 9. And when you prove two triangles congruent to each other, it means that all the corresponding angles and sides will be equal to each other. So this is what we're going to do. We're going to prove that these two triangles, triangle OXY and triangle OZY, is congruent. And like I said, we did it in grade 9, so make sure you know the layout of proving similarity and congruency, because also in the past 10 years, I cannot think of a past paper that I've written that in grade 12 now, a grade 12 final paper that did not contain congruency. I think it is literally in each and every, so you will, 99% sure of it, you will have to do congruency at the end of grade 12, your final paper. Okay, and congruency basically has a set structure that you can just follow, okay? And the first being you say in which two triangles you're working. That's easy enough, okay? And then you have to list 3 things that are equal, but for congruency, these 3 things, there must be at least one of them must be a side, okay? Because when you prove similarity, the structure looks exactly the same, except it's always 3 angles, okay? And with congruency, at least one side. Now let's look at the first thing. What's the first thing that we can see is equal? And that is that OX is equal to OZ, because that's the radius, okay? And this is also a small thing that we often, or it's easy to miss. When you're looking for things that are equal, we often forget that, oh, but the radius of a circle is equal everywhere. But I will show you an example of that in a question a bit later. Okay, and then the next thing, we have that OY is equal to OY. So that is going to be this side here, which is common to both triangles. So obviously it would be equal to each other or itself. And then finally, we have that OYX and OYZ. So these two angles are obviously both equal to 90, which makes them equal to each other. And that is basically given. Okay, and then finally, when we have those 3 things, we can state therefore triangle OXY is congruent to triangle OZY. And our reason is, and remember there's 4 reasons. Go and recap or watch a video on that if you don't know how to do this. But one of the 4 reasons is if you have a triangle with a right angle, the hypotenuse equal, and another side equal. The reason is right angle, hypotenuse, and side RHS. Okay. Now we have proven these two congruent to each other in that, and then we can simply just state therefore XY will be equal to YZ because they are the corresponding sides in 2 congruent triangles. All right, and then we have proven that OY bisects YZ. Okay, so actually if you understand where this comes from, this is actually not so hard. It's basically construct lines, prove the 2 triangles congruent, and therefore the 2 corresponding sides will be equal. Okay, and that's that. Then going on, the converse of theorem 1. So the converse states that a line drawn from the center of the circle to the midpoint of a chord will be perpendicular to the chord. So in theorem 1, we saw that if the line is perpendicular, it means it's going to bisect the chord. In this case, we say that if it's bisecting the chord, the line will be perpendicular. So this is basically just a converse saying that if I hand you a circle with midpoint O and there's a chord X, a Z anywhere in the circle, and I tell you draw OY, this line, your only condition for that line needs to be that wherever the line cuts your chord, it has to bisect the chord, it has to cut it in half. And when you do that, and after you've done that and you measure this angle, you will see that this angle is 90 degrees. Okay, so that's what the converse of theorem 1 says. And your reason is line from center to midpoint of chord. That's if you ever use this theorem. Okay, and in what scenarios would you use it? You could get like something like this. Okay, so they basically just show you that these are equal, and you have to maybe, let's say there was a line here and there could be like a let's say that was like a 60 degrees over there, and you have to solve for this angle, then you can say that this angle must be 90 and give this reason, line from center to midpoint of chord, to prove that that is 90, and then you can use angles of a triangle to basically get the third angle. But that's just one of the examples where you can use this theorem. Okay, so that was theorem 1. Let's go to theorem 2. So theorem 2 says the following: the perpendicular bisector of a chord passes through the center of the circle. Okay, let's see how that applies. Now, I give you a circle. We don't know where the center is, okay? We basically just know that we've got chord DF, okay? And I tell you, draw a line that bisects DF, okay? So it has to cut DF in half, but this line must also be perpendicular to DF, right? If you do that, your line will inevitably go through the center of the circle. So you'll still not know where the center is, but you will know that your line goes through the center. And the reason is perpendicular bisector of a chord. Okay, now theorem 1 is more common. This one I haven't seen a lot in questions, but it is there. It's just not that common. Now let's look at the proof. So this is our sketch. Then what are we given? The two things we were given was that it is the midpoint of DF. Okay, and then also that GE is perpendicular to DF. Okay, now what do we need to prove? We need to prove that GE passes through the center of the circle. Okay, now in this proof, we are also going to do a construction. So we're also again going to construct lines DH and HF. Now, the difference between this is, remember, we don't know where the center of the circle is. So this, wherever you construct, you can even construct it here at the top, it doesn't matter. As long as it's like that point H lies on the line. Okay. And before we continue, once again, I just want to give you a heads up of where we are going so that you can kind of see the overall picture before we just dive into it. So what we want to do is, after we've constructed these, again, we have these two triangles, okay? And what we want to prove at the end of the whole thing, we want to prove that DH is equal to HF. And why do we want to do that? Because we want to prove that any point on this line, wherever it lies, will be equally far away from D and F, okay? And we know that the moment the point leaves the line, let's say we just move a little bit to the right, immediately DH will be bigger than HF. And if we move a little bit to the left, immediately HF will be bigger or longer than DH. So for any point on this line, the distance between these 2 points will be equal, but also for any point off this line, the distance will be unequal. And we know that whenever we hit the center, the line from H to D and H to F will be the radius. And therefore, we know that they must be equal. And therefore, we know that if they definitely are equal, then the line must be going through the midpoint, or the midpoint must lie on that line. Okay, so let's look at the layout and the structure, or how we're going to do that. So first of all, what we're going to do is just going to prove these two triangles are congruent, because then we can show or say that DH is equal to HF, and then we just need to get our wording right to say that the midpoint lies on the line. Okay, so first of all, when we do congruency, we just list that in triangle HDE and triangle HFE, that's the two triangles we're going to prove congruent, and then we list our three things. So HE is equal to HE, that's the common line lying between the two triangles that belongs to both triangles. Then the second thing that's equal is DE and EF, and that's obviously given over here. This is equal to this because that was one of the conditions of this line, that it has to cut DF in half. And the other condition obviously was that E1 is equal to E2 is equal to 90. That was also given as one of the conditions. Then we have our three things that are equal, so we can end off and say, therefore, HDE is congruent to HFE, and our reasons is side, angle, side. Okay, in that order. Then we can conclude that DH is equal to HF. Okay. Now, just to continue with that, we can say that H is always equidistant from D and F. Okay, basics, straightforward. Then the center of the circle is equidistant from D and F. Okay, that is a fact because they both lie on the radius and the center is in the center of the circle. And with those two statements, we can therefore conclude that the center of the circle must lie on GE. Right, that's the proof. Right, so theorem 1 and 2, the theory is done. Now let's look at applying it in questions. Now for example 1, it is given that PR is 12, so that's not indicated, so we'll just indicate that here, so that's 12. Then QS is 2 and PR is perpendicular to OQ. PR perpendicular to OQ, so also going to just indicate that there. Alright, so now we can just focus on the sketch as we work through the correction. Now, first of all, we want to solve for x, and when you see a right angle triangle and you're kind of looking for sides, I'm hoping you're already thinking Pythagoras. And that means we need PS and we also need OS. Okay, so what we can also do, and like I've mentioned earlier, what we tend to miss is that the radius is everywhere the same. So OP is the radius and also OQ, which means they are the same length, which means that OQ is also equal to X, all right? And we're going to use that because if I want to find OS, I can either find the actual value, and if I can't find the actual value, I can find it in terms of X and use that in my Pythagoras theorem. So if we know that OQ is X, in terms of X, OS is X, the whole length, minus cutting off the QS, which is 2. So this is going to be X minus 2, all right? And then to find PS, we know that the center of the circle and the line from the center of the circle is perpendicular to this chord, which means it bisects the chord, which then means that PS is equal to SR, which then means if PR is 12, it means that PS is 6. All right, so now we basically have everything we need in order to solve for X using Pythagoras. Now to start off, let's put everything that we've just said on paper. So we have that PR is equal to 12, and that is given. All right. And then we can therefore deduce that PS must be 6 because of the first theorem, which states that line from center is perpendicular to chord. So line from center is perpendicular to chord. All right. So there we have that. Now from here, we said that OQ is also equal to X because of the radii. Okay, and that makes OS equal to X minus 2. Right, no reason there, that's just logical procession. So then we can use this triangle and we can say that X squared, which is the hypotenuse, so X squared is equal to the other two short sides added together, also squared individually. So we've got 6 squared plus X minus 2 squared, okay? This whole length here. Now, to simplify this, or to solve for X in this case, we have to start by multiplying out these brackets. So I'll write X squared is equal to 6 squared plus. Now be careful not to just multiply or square both of these terms directly. You can only do that if they were multiplied together. So either one of the two ways, expand these two brackets, like write it as x minus 2 next to each other and FOIL it out. I'm going to use the faster method, and you square the first term, multiply the two terms together and double it. So minus 2x doubled is minus 4x, and then square the last one, so plus 4. All right. Now this looks like a quadratic equation, but with quadratic equations everything goes to the one side, right? Because of the x squared. But what I can also see is if I take this x squared to the other side and it becomes a negative, we've got x squared minus x squared, which means these two will add up to 0, eliminating all the terms that contain x squared. In that, and that means that this equation will now become a linear equation, and with linear equations we only take the terms containing x to the left hand side. So I've taken this one over as well, and we keep the constants on the right hand side. So this is 36 plus 4. Okay, this becomes 0, so we're left with 4x equal to 40, and then divide both sides by 4, so x is equal to 10. Okay, that is our answer there. Okay, now for question 1.1, make sure that you have paused this, try it on your own first, and then look at the memo. Now, given that PR is 6, and once again they didn't indicate it, so we can just indicate it on our sketch. PR is 6, and OQ is 4, determine the value of x. Okay, this is quite an easy one. We know this is the center of the circle, and the line from there is perpendicular to this chord, making this PQ equal to QR, so that is equal to that, and therefore we know that this is 3 because it's half of PR, and this is a very easy triangle to use Pythagoras in. So we'll just say that x squared is equal to 3 squared plus 4 squared. Okay, but let's start from the beginning. We know that PR is equal to 6, it's given. Okay, and then we know that PQ is equal to 3 because of the line from center is perpendicular to chord. Okay, now we can use Pythagoras, so we can say that x squared is equal to 3 squared plus 4 squared, Pythagoras, and solve for x. We square root both sides, and then we have 9 plus 16, and that gives us the square root of 25, and that's just equal to 5. So this is easy to do without the calculator. Normally we do our Pythagoras with the calculator, but that one works out nicely. Okay, that's our answer. Then next we've got question 1.2. So DE is 8 units and DB is 12 units. We've got DE and we've got DB. Then calculate the value of x. So x is OD. Now, first of all, remember the radius. Okay, so OE is the radius, which means it will also be equal to OA, and it will also be equal to OB. And the radius in terms of x, if that's x and that's 8, then the radius is simply going to be x plus 8. Okay, and next we have all three of these sides, but now we're not given that this is a right angle triangle, but what we do know is that AD is equal to DB and AB is the chord, and that is a line from the center of the circle bisecting that chord, which means the converse of theorem 1 says that this must then be perpendicular. Okay, so let's write that down. So first of all, we can start by saying that x plus 8 is OB. Actually, we want to write it as this. We want to say that OB is x plus 8 and just say that it's the radii. Okay, then we want to say that AB is perpendicular to OD. Okay, and our reason is the converse of theorem 1, which says line through center and midpoint. Alright, line through center of the circle and midpoint of that chord. Now we can say, therefore, we know that ODB, the angle ODB, is equal to 90 degrees. Okay, now we can use Pythagoras. So we have that our hypotenuse side is OB, so I'm going to start and say that x plus 8 squared is equal to x squared plus 12 squared. Okay, so this is Pythagoras. Okay, now we just need to solve for x. So again, I'm going to use the fast method, x squared plus multiplied together is 8x, and then multiplied by 2 is 16x, and square the last one plus 64 is equal to x squared, and that becomes 144. Okay. And once again, if I take this to the other side, it's going to eliminate all the x squared terms. So taking that over and leaving the constants, or taking the constants to the right hand side when it's only a linear equation. So plus 16x equals to 144 minus 64. So this is then 16x equal to, now 140 minus 60 is 80. Okay. And then we divide both sides by 16. So either with a calculator, obviously when you're doing this in a test, just do it with a calculator. But if I divide both sides by 8, I can see this is going to become 2x equals to 10. And then if I divide both sides by 2, I just have x equal to 5 again. All right, and that is the answer. Next, question 1.3. If AB is 48, OC is 7, OM is 5, calculate PQ. Okay, now this one is interesting because we have a chord over here and we've got information over here, but we need to kind of work our way through to this chord. And what can be the connection between the two? And the answer is the radius, because OA is the radius and also OP is the radius. So if I actually find OA using Pythagoras, then I have OP, and then I can work my way through OP and OM and use Pythagoras to find PM, and then obviously that's half of PQ because we've got the line from the center of a circle perpendicular to the chord. Right, so let's start and say that AB is 48, and that is given to us. Okay, next we can say that so this bisects the chord, OC bisects the chord, so therefore AC will be half of 48. So AC is 24, and our reason is the first theorem, which says line from center. So line from center is perpendicular to chord. All right, and then if we know that this is 24, we can use Pythagoras to find OA, and OA is the hypotenuse, so OA squared is equal to 24 squared plus 7 squared, and this is the Pythagoras theorem. And then we can just square root both sides, so OA is equal to the square root of 24 squared plus 7 squared. Okay, and then we can put that onto the calculator. So you have the square root of 24 squared, let's go back, 24 squared plus 7 squared. So 7 squared is equal to 25. Okay, so that's 25 over there. So if OA is 25, it means that OP is also 25. So OP is equal to 25, and our reason is radii. Okay, 25, 25. Then PM, using the Pythagoras theorem, we've got PM squared. Now, PM is not the hypotenuse, so we've got OP, which is the hypotenuse. So that's 25 squared minus the other shorter side, so which is 5 squared. We just write Pythagoras. Okay, and then to solve for PM. So PM is the square root of 25 squared minus 5 squared. And we put that onto the calculator. So square root of 25 squared minus 5 squared is equal to 10 square root of 6. Okay, now we know that this OM bisects PQ, which means that PQ must be double this, so it's going to be 20 square root of 6. Now, also, if this question especially didn't state that you need to leave your answer in simplest third form, if you are working in an exam or test, remember the instruction says that if they don't state anything, then you have to round it off to 2 decimal places. So always just be safe. So that's going to be multiplied by 2, And even if you're not sure, like, just also give your answer into decimal places. So this is 48,99. So equals to 48,99. Okay, and then moving on. So example 2, in the diagram below, SU is 5, and then PT is 8, and then PO is 10. Calculate the value of X. Okay, so let's look at what we have here. Now, first of all, PO is the radius, so meaning that all of this is also 10, this line over here, and OQ is also 10. Okay. Then also, what do we have that OU is perpendicular to SQ, which means it bisects that chord. It also is perpendicular to PR, which means it bisects this chord over here. And we need to find X. Now, how to find X? If we know this whole line over here is 10, and we can find OU. If we know what OU is, we can just subtract that from 10, and that would leave us with X. All right. So how do we find OU? Now OU lies in this triangle. So this triangle is a right angle triangle. So if we know this side and we know this side, we can obviously find OU with Pythagoras. Okay, but we do know that this is also 5. We've seen that this is also the radius. So now going ahead to find OU. But before that, let's just put everything on paper that we have done so far. So we've got that OQ is equal to 10, and our reason is radii. Okay, we also know that UQ is 5, and our reason is the first theorem, which states line from center is perpendicular to chord. Okay, now to find OU squared is the hypotenuse squared, 10 squared, minus this side, 5 squared. So that's Pythagoras. And then OU is the square root of 100 minus 25. Okay, let's put that onto the calculator. So the square root of 100 minus 25, and that gives us 5 square root of 3. All right. Now, to find X is simply going to be the entire radius minus OU, which is 5 square root of 3. We can just put that onto the calculator again. So we have 10 minus, and I'm just going to say minus the answer, because our final answer was 5 square root of 3. And that is equal to also this, because this is the simplest third form. But if we put it to decimal places, we've got 1,34. So 1,34. All right, that is our answer there. Then for the last question, for question 2, given that QP is 24 and PR is 25 and OT is 5, determine the value of X, and X is this OS. So let's just talk through this again. We only have this chord's length, and we want to work our way up to here. And again, the connection between the two is the radius, all right? Because if I can find OQ, that is the radius, I can also find OR, which is the radius, and then solve for X with Pythagoras, all right? Now, we can start off by saying QP is 24, which is given, and then we can see that from the center of the circle, this line is perpendicular to the chord which bisects it. So this is equal to this, which makes this 12. Okay, and then using Pythagoras, we're going to find OQ. So to start, I'm going to say that QP is equal to 24 because it's given. Okay, and then we can state that QT is equal to 12 with the first theorem, which is that line from center to chord. So line from center to center is perpendicular to chord. Okay, and then what I'm going to do is to use Pythagoras. So QO squared is equal to 12 squared plus 5 squared. Pythagoras, right? And then QO is the square root of 12 squared plus 5 squared. Okay, and then put that onto the calculator. So square root 12 squared plus 5 squared is equal to 13. Okay, so if this is 13, then this is also 13 because of the radius. So Q or OR is 13. And reason is radii. Okay, and now we can see that PR is 25. So PR is 25. That's given. Okay, and then SR is half of that, which is 12,5. And our reason again, line from center is perpendicular to chord. Okay, and if we know that this is 12,5, we use Pythagoras to solve for x. Okay, so x squared is equal to the hypotenuse, which is 13 squared, minus the other side, 12,5 squared. Okay, Pythagoras, and then square root both sides. So square root of 13 squared minus 12,5 squared. Definitely going to do this with a calculator. So 13 squared minus 12.5 squared. And to 2 decimal places, we've got 3,57. Alright, and that is done. So basically we've done the final section and then we're done with this lesson.